So we now continue with the proof of the theorem. We have done the following. We took, this is where we had stopped in the last lecture, which is that we had a finitely generated graded module, and we had this map which was multiplication by xn to m. This shifts degree by 1. Degree j part here goes to degree j plus 1. And then we had co-kernel of phi and kernel of phi. So this is the situation we were in, and we wanted to prove that by induction we wanted to prove that the Hilbert function of m agrees with a polynomial in sufficiently large degrees. Okay, and not just that it agrees. It's a linear combination of z linear combination of the polynomial, the binomial polynomials x choose k. Okay, if we take degree j part here, it gets multiplied to degree j plus 1, and then degree j part of the co-kernel and degree j part of the kernel. Okay. So notice that hm of j plus 1 minus, so let's call this thing c and this is k, and the observation was that c and k were are modules over R adjoint n minus 1 variables. Okay. Hm of j, this is h just means length in that degree. Okay, it's just a notation. So hc, so depending on how you grade it, it would be either j or j plus 1, but we'll just call it j. So we are taking this, subtracting the length from here, okay, and then on this side we will have kernel. So if you have any, so this is an exact sequence. Okay, so sorry, let's go back a little bit. This is an exact sequence. If you look at elements of degree j that go to 0, that will, okay, so that's here. Then here we look at elements of degree j plus 1, and here we get some, depending on what you call c, either degree c or degree j plus 1. So we would get something here. So the alternating sum of their lengths should be 0. So that's a property about an exact sequence of finite length modules, which we will work out in an example, in an exercise. Okay, so here there's a degree j part of this, degree j part of this, degree j plus 1 part of this, and degree j part of this. Okay. In that sequence, all kernels are equal to all images of the previous map, and hence the sum will alternate, and alternating sum would be 0. And so in that case, so we are taking the length of this minus this minus this. So alternating sum means length of this minus this plus this is equal to 0. In other words, length from these two parts, this and this, will be equal to length from these two parts. Okay, and so this is, and when we rewrite it, we would just get hk of j. Okay, so this is from the fact that this is an exact, in each degree this would give an exact sequence. But bear in mind that there is a change in degree for this map. Okay, so we get this one. Okay, so now, so now what do we know? So this is by induction. Okay, this is of the form. So by induction, this is a function which agrees with a polynomial of that form. Okay, so this agrees with. By induction, this is equal to, okay, so its value agrees with, value is the same as that of some combination EI, PI, okay, evaluated at J. I goes from 0 to n minus 2. Okay, remember these are in n minus 1 variables, so this is what we would get for all sufficiently large J. Okay. So this function itself are not polynomials. It is only for all sufficiently large values that on the right side this agrees with the polynomial. Okay, so now here is an exercise which I will outline how it should be done with hints. Here's an if f from z to z is a function such that f of j equals some such that there exists some e0 through ek e0 through ek such that I from 0 to k such that delta f of j agrees with ei pik pij. So delta f agrees with this polynomial for sufficiently large j. So this is the delta of the function of the Hilbert function. This is the first difference of the Hilbert function. Okay. So to finish the proof, we will have to prove, or one way to prove would be that if the first difference satisfies this property, then the function also satisfies that property. Okay, so that's what we will. So that this will be an exercise. It will be done in a way similar to the lemma was proved, and I will outline the steps. Okay, such that this thing, then. Okay, f2 is of that form. That is for all sufficiently large j, fj will also be some integer linear combination of pi evaluated at j. Okay. So this you will do the exercises, not very difficult, once we understand what happened in the proof of the lemma, and so that is the end of the proof. Okay. So the difference is, the first difference of the Hilbert functions satisfy that by induction, and hence Hilbert function also satisfies that property. Okay, so the precise precise nature of these coefficients we will not worry about. In this course, but they are also of interest in various contexts. Okay, so now let's look at yeah. So recall that this polynomial is called the Hilbert polynomial of M, okay, over S as an S module. Okay, and note also that degree of the Hilbert polynomial of M is at most n minus 1. That it is one less. It is at least one less than the number of variables. Okay, we would need this information a little later. Okay, so let's look at a Macaulay example. Okay, so this is a calculation about the Hilbert polynomial. So we ask Macaulay. So the relevant functions are Hilbert function with a camel case. So f is uppercase, h is lowercase, and so again, so z is a polynomial ring in one variable. Apply 10. So this means integers 0 through 9. The function j goes to. So I just for printing, I just want to print it as a. If I want to print j and the Hilbert function just for reading it. So it says in degree 0, it is 1, degree 1, it is 1, degree 2, it is 1, and so on, which is what is expected because this is the basis for that is x to the j. Okay, so in each degree it is going to be 1, and we ask for its Hilbert polynomial, and it gives a list. It gives p0. Okay, and it says projective Hilbert polynomial. Let's not worry about it now. It has to do with. I mean, the word has to do with some projective geometry and which we will come to later, but right now we just, so this P0 is what we defined as P0 in the lecture. So Hilbert function gives the length of the module in a specific degree. So make it a habit, if you see a command in Macaulay 2 that you don't know, make it a habit to look at its help. Okay. Look at its help or its methods. That will tell you in which ways you can use it. So P0 is a Hilbert polynomial of a polynomial ring in one variable. Okay. So this is what we had. Okay. It is the constant polynomial 1. Let's look at the ideal x in R. We ask I is ideal x, and then we ask the same question, apply I, j goes to j, comma Hilbert function j, comma I. And just notice that for every j greater than or equal to 1, it is actually printing zeros. The first, in any ordered pair, the first is just j itself. Second one is the value of the Hilbert function. It prints zeros. So actually it is not the Hilbert function of I, it is the Hilbert function of the quotient that it is printing. So please remember this. We ask for its Hilbert polynomial, and it prints 0, and it says a projective Hilbert polynomial. It's a constant polynomial 0. Again, it is of the quotient. Okay. We ask polynomial ring in two variables. Polynomial ring in two variables, and ask for its Hilbert polynomial, and it says P1. Okay. So this same notation as what we were using in the lecture. Pn is the Hilbert polynomial of the polynomial ring in n plus 1 variables. Okay. Now we ask Hilbert polynomial of the ideal generated by x square and xy, and so we get, so remember the ring is this in two variables. So if you kill this ideal in degrees greater than or equal to 2, x power of x won't be there, and in degrees greater than or equal to 2, mixed terms involving x and y won't be there. Then for the only thing that will be left is just powers of y. So is spanned by y to the j. So it's again the constant polynomial 1, and therefore we get P0. That's what it said. Hilbert polynomial of, remember this is in the quotient. So Hilbert polynomial of this is P0. Now we change the ring just a little bit. Okay. X, y, z, and x squared, xy, same polynomial. Okay. Hilbert polynomial in polynomial of I. So then we get P0 plus P1. Remember in the quotient now there are also terms that would involve z. Okay. So there will be powers of y, and every multiple of z will be there in the quotient. So we get a different Hilbert polynomial, P0 plus P1. And so this particular thing I have asked, just for that one could refer to it later, I have called it Pi, small p capital I. And in this here we ask for integers 0 through 9, print the, list the values. This is just to keep track of the degree in each of these in the output. First give the Hilbert function of the quotient in degree j, and then give the value of the Hilbert polynomial in degree j. Okay. So out here we suddenly see that the Hilbert function does not agree with the Hilbert polynomial value. This is the correct one because it's in degree 0. All that is left is the field, so it has to be one dimensional, and this 2 is some, okay, it is a value of the polynomial. It need not be the Hilbert function, but in this particular case hereafter it agrees with the Hilbert polynomial. In degree 1 there are 3 polynomials. It's a rank 3 vector space. It's spanned by x, y, and z, and the polynomial also takes value 3. In degree 2 there are 6 degree 2 vector space in 3 variables is 6 dimensional, in which we have killed 2. So in the quotient there is 4, and that's what it shows here, and then one can this. Okay. So it grows up linearly, and that's why there is a P1. Okay. It grows linearly because we have not done anything to z. So every multiple of z is there forever. So the rank grows linearly, and we see that in the P1. Okay, so now we use these ideas to study local rings, Noetherian local rings. We use these ideas to study Noetherian local rings, and so the thing is called Hilbert Samuel polynomial. So Hilbert polynomial, the study of this Hilbert function, etc., goes back to Hilbert graded rings. So the beginning of the 20th century or around that time, turn of the century, from 19th to 20th. But the idea, local rings, their structure, etc., were all from the middle of the last century, Samuel and various other people. And so this is called Hilbert Samuel polynomial. Okay. So here is a theorem. So let me state the theorem and then we'll try to set up and then prove it. Let Rm be a Noetherian local ring M a finitely generated R module, I an M primary ideal. Remember, saying that the radical of I is a maximal ideal is the same thing as saying it is primary to that maximal ideal. So we often write it and might just say M primary ideal. Okay. Then there exists a polynomial, okay, P, which depends on I and of course on M, okay, T inside with rational values, okay, such that for all n, for all j sufficiently large, maybe let's call it n, for all n sufficiently large, the length as an R module of M mod I to the n plus 1 m is given by this polynomial. Okay. So this is sort of a similar flavor as the Hilbert polynomial theorem, except there are no graded ring structure at this point. It is just a local ring and modules over it and then quotients. And the module that we will consider is this quotient, m mod I to the n plus 1 m. Okay. So the okay, so this is the thing. So let's define this. PIM is called the Hilbert Samuel polynomial. Polynomial of M. Okay. Yeah. So when we prove it, we will get some idea of what the okay, what I mean how many degree, etc. Okay. So that's okay. Okay. So in order to prove the statement, we need to introduce a new object. Okay. So let R be a Noetherian ring, M finitely generated, and I an R ideal. Okay. Then the associated graded ring okay, which we will denote by this, okay, is the ring, is a graded ring. Okay. Direct sum of I n mod I n plus 1 n non-negative. So here I to the 0 by definition, by that we mean R, okay, in which multiplication is given by multiplication is given by okay, so this is going to be a graded ring, so we will define multiplication for homogeneous elements, okay, and okay, A bar times B bar, okay, we'll say what A and B are in a minute, is equal to AB bar, where A is in I to the n, B is in I to the m, A bar is its residue in I n plus 1, mod I n plus 1, B bar its residue mod I m plus 1, and AB is automatically an element of I to the n plus m, but AB bar is its residue, its meaning residue of A. So maybe you should, okay, residue of A in this is residue of B, and this is residue of AB in I n, not n, in mod I n plus n plus 1. Okay. So this is the definition of the associated graded. Addition is just, these are all abelian groups, okay. So this is what we can. So what we need to do is multiplication. And the observation that we would like to make at this point is, okay, if x1 through xm inside I generate I as an ideal, then if x1 up to xm in I generate as an ideal, then there exists surjective ring homomorphism R mod I. This is the degree 0 part of the associated graded ring. Put variables, enough of m of them, to the associated graded ring. Xi goes to little xi. Okay. So this is the property. This need not be an isomorphism. There could be there could be kernel, things in the kernel, but there is definitely a surjective homomorphism, because in any degree all that we need to generate is something, some power of some product of these generators, and there are linear combinations, but for the R linear combination we may as well assume that they are elements not inside I, so you can work with the residues. And for getting the powers, products of the generators, one can just use this map. Okay, so there's a surjective homomorphism is what we use. Okay, so now let M be a finitely generated R module. Okay, then we can construct the corresponding associated graded module given by direct sum of I n m modulo I n plus 1 m, and this is n plus 1. This is again n greater than or equal to 0, and m itself is not a graded module. R is some Euclidean ring and m is a module over it, from which we can get this graded thing. And here again, when we say I0 m is by definition m, it is just R. Okay, so this is, we get this thing. Okay, so now putting these, so the observation is that so we are assuming that m is finitely generated. So then the associated graded module is finitely generated module over the associated graded ring. Okay. So this is where, okay. So now let's prove the theorem. Okay, so recall the theorem was theorem was here. We need to look at, sorry, this is not M prime, this is just, we need to look at M mod in plus 1 M. So the length of this, okay, so proof of the theorem. Okay. So length of M mod in plus 1 M is the sum of the lengths, let's say I goes from 0 to n of I to the im modulo I to the I plus 1 m lengths of these things. Okay, that is because this can be proved by induction on n. So let's look at the last step in the induction. Okay, so the last step in the induction would be M mod in plus 1 m surjects onto, so let's write it as a short exact sequence, M mod in m. In m is bigger than in plus 1 m or not smaller. So therefore, there is this surjective map, and the kernel of this map is in m modulo in plus 1 m. Okay, so recall that in the theorem I is M primary. So in m mod in plus 1 m is finite length. Okay, so we can talk about length, and then by induction this is equal to the corresponding sum all the way up to n minus 1, and then for n we add this, we get the length of this thing. All of these are finite length modules. Length is additive in an exact, short exact, I mean the middle length of the middle one is the sum of the lengths of the outer two, and therefore the length of this is these two, and then by induction one can show this. Okay. So now there is a polynomial. So notice that this is the graded part of so this im mod in plus 1 m, this is the graded ith graded part of the associated graded module, which is a module, finitely generated module over a polynomial ring over the polynomial ring over R mod I, which is Artinian. Note that R mod I is Artinian, okay, and the associated graded module is finitely generated module over R mod I adjoint x1 through xm, okay, where m is such, where m is such that I has a generating set. Of m elements. Okay. So this is a finitely generated module over that, and hence okay. So therefore, by the previous theorem, which is about the existence of Hilbert polynomial for modules over such rings, okay, each degree p is eventually is given by a polynomial, and using the same argument as earlier, this length is also given eventually by a polynomial. Okay, there will be an initial part where the polynomial won't agree, but afterwards it will agree with the polynomial. Okay, so now, therefore, now use the previous result. So maybe I should just write, therefore, the function j going to length over r of I to the j m mod I to the j plus 1 m is given by a polynomial for all sufficiently large j, which now implies that the function j goes to the length over r. So this was the length over r or r mod I. Okay, it's the same. R of m mod I n plus I j plus 1 m is given by a polynomial. For all sufficiently large j. Okay. So this is the end of this proof. Okay. So in the next lecture, we will prove that the degree of the polynomial does not depend on the ideal. Okay. And that is therefore an invariant of the module itself. And then we will relate these two dimensions. So that is that will be in the next few lectures.